Good day, everybody. In today's lecture, I'm going to explain to you first how to correctly record the data in the measurement, and then I'll talk about how to convert one unit to another. So let's dive in. In making any measurements, you must pay attention to both the numbers and the unit. A number without a unit doesn't make sense at all. If I ask you how tall that building is, you tell me it's 120. What does it mean? Does it mean 120 meters? Does it mean 120 inches? 120 feet? So you have to include both a number and a unit. About the number, there are many different ways to record the number. For very small or very large numbers, we use so-called scientific notation to write it. For example, 1.2 times 10 raised to negative 10. The 1.2 portion is called this decimal part. And the exponential part is 10 raised to negative 10. And negative 10 is so-called exponent. Do remember, for the standard scientific notation, the decimal part is always between 1 and 10, but smaller than 10. So this number, let's call this number A, pre-exponential, it sometimes is also called a pre-exponential number, or the decimal part. So this A must be in between 1 and 10, but smaller than 10. So let's look at how we can write a very large or small number using some specific examples. For example, 5983. If you want to convert it to standard scientific notation, first you do know the original decimal point is where you see in this dot. Then you have to move the decimal place to right after 5, because we do know the pre-expo number must be in between 1 and 10. So we count how many times you will have to move the decimal point. So you will have 5.983. So you move it 1 time, 2, 3 times, then you will have the decimal point to where you need it to be. So do remember one thing, after you move this decimal point, the number has changed, and this number in the box apparently is smaller than the original. To compensate this change, when you write 10 raised to the exponent, this number is a positive number. So that's why it's 10 raised to negative 3, because 5.983 is smaller than 5983. So that's why it's 10 raised to 3, not negative 3. So in contrast, you look at the number to your right side. You have 0.00034. Do remember, before you do conversion, you do recognize the pre-expo number or the decimal part must be between 1 and 10. So you do know the decimal point must be moved to this area. You see that dot over there? Then we count how many times you move the decimal point. So after you count it, you do know this is 1 time, 2, 3, 4. All right? You have different ways to count it. Whichever way you prefer, it's good for me. So you move the decimal place 4 times. Do remember, to avoid mistake, you got to write the correct exponent. Why is it negative 4 over here? Again, I use the same trick. The original number in this circle apparently is much smaller than the number that is listed as 3.4. So for this reason, to make 3.4 smaller and equal to the original number, 10 is raised to the negative 4 rather than positive 4. So hopefully you will not make this type of mistake. Let's look at one question. In this question, we want you to convert this specific number to scientific notation. So let's do this step by step. 0.000459. So you want to convert it to scientific notation. Do remember, scientific notation must have a decimal part or pre-exponent number in between 1 and 10. So you write that first. Then it's 10 raised to a certain number. So what is that number? So let's count how many times you need to move the decimal point. 1, 2, 3, 4. So apparently it's 4 times. But is it positive 4 or negative 4? So do remember the same trick you're going to use. This number, original number, is way smaller than the decimal part, 4.59. So for this reason, it's negative 4. 10 is raised to negative 4. So apparently D is the correct answer. All right. So I'm going to emphasize one thing. How do you avoid mistake when you try to convert a scientific notation to a decimal number or a decimal number to scientific notation? I want you to compare the magnitude on both sides, especially between the original number and the pre-expo or so-called decimal part of the scientific notation, so you can avoid making simple mistakes. Now, let's go on and talk about how to report the scientific numbers in the real measurement. You might see some numbers like this one, 45.872. The last digit and the last digit only is estimated. So in this case, we have 1, 2, 3, 4, 5. As you see, 1, 2, 3, 4, 5 numbers over here, which we call significant figures. We'll go into the details about how you count these numbers later on. So what we're going to do right now is to tell you how to actually do the recording. When you look at these two rulers over here, apparently the ruler over the top is more coarse, the bottom is more precise. How do you actually do the reading? Of course, when you do the reading, you make sure you start with the 0 over here. Let's say you have an object that is as long as maybe this. All right. So it's like this. So how would you record a number? So here's the steps you should follow when you try to read this correctly. First, you find the smallest increment. Then you read one more digit. It's not one digit, it's one more digit past it. Okay. So, let's move back. For example, on the top one, the smallest increment, which means how much it represents between the neighboring lines. Apparently, between these two lines or any other two lines over here, that's 1 centimeter, right? That's 1 centimeter. That's the smallest increment you see over here. Before I continue, I would like to introduce to you another concept, which is so-called decimal place. Let's look at these examples. .1 centimeter, 1 centimeter, 0.01 centimeter, 0.001 centimeter. Okay, so this concept is so-called a decimal place. decimal places. So what is decimal places? The decimal places are the number of digits to the right side of the decimal point. So where's the decimal point for 1? Apparently it's 1.0. So the decimal places, or you simply call this dp, it will be 0 dp for 1 centimeter. 0.1 centimeter has decimal place over here in the triangle area. You see the decimal place, the decimal point. You have 1 digit to the right side of a decimal point. So you have 1 dp for this one, or 1 decimal place. Similarly, 0.01 centimeter has 2 decimal places. It's 2 digits to the right side of the decimal point. The next one has 3 dp. So in the real measurement, the first step, you find the smallest increment, okay, and in terms of how many dp you have, how many decimal places you have. Whoops. So this 1 cm has 0 dp, 0 decimal place, or no digits to the right side of 1. And you read 1 more digit to it. So you do know your result. Oh, why is it moving? Your result will have 1 more dp, which means your result will have 1 decimal place. So before you read anything, you know the format you should be recording. So before I give you any object to measure, and I give you this ruler, if you report to me a different format, I will know it's wrong. For example, as we analyzed over here for the top ruler, it should have 1 decimal place, which means the recorded number should be a certain number on the left side in decimal place, and the 1 digit, I'm going to use hashtag to represent cm. So if you report to me something like 2.45 centimeter, I know it's absolutely wrong. I don't even have to ask. You don't want to complain to me, hey, Dr. Yan, you haven't even looked at my measurement. I don't have to. Why? Because I know which ruler I give you. I know what format of the results I expect to see. So let's read this one. So we know on the top one, the length is between 2 and 3. Okay, so it's 2 point something when we read it. It's 2 point, but in between 2 and 3, you have no more increments. So you will have to mentally divide between 2 and 3 into 10 increments and decide on which imaginary line it falls on. To me, I think it's probably 2.7 centimeter. But if you have more students, some students might say it's a little bit to the right side of the middle, so I'm going to record it as 2.6 centimeter. And some might say, I think it's a little bit more than that. It's 2.8. All of these numbers will be considered as correct. As you notice, the last digit is slightly different. That's why the last digit and the last digit only is the estimated number. Let's look at the bottom ruler. With the same length, as you see, the smallest increment, let's do the same way, the smallest increment is smallest increment over here is 0.1 centimeter. So when you look at that, for example, that's between this line and that line. How much is that? That's 0.1 centimeter. Between the neighboring lines, the amount it represents, that's the smallest increment. So in this case, that's 0.1 centimeter. And before you start measuring, I want you to always analyze the ruler first. Find out the number of decimal places in that smallest increment for this instrument, then you know the format of the result should have one more decimal place. Then you will never make a mistake again. So for this result, apparently you would have, again on the left side you don't know, but to the right side of the decimal place we do know you must have 2 digits represented by 2 hashtags. Don't forget the unit. So if I give you ruler B, similarly, if you report a number like 2.5, 2.6 centimeter, I know for sure it's wrong, because for ruler B, you should always see 2 digits to the right side of the decimal point, or 2 decimal places. So let's read this one. Apparently, each one represents 0.1, so 2.1, 2, 3, 4, 5, 6. It's between 2.6 and 2.7. So in my eyes, I mentally divide this neighboring lines into 10. I think it's almost right in the middle. So I'm going to record it as 2.65. Don't forget the unit. And again, some students might read it a little bit differently. It might be 2.64 centimeter. It's also correct. Also, or 2.66. It's also considered as correct. Now let's go over some more difficult situations. For example, if the length falls, let's look at over here. Let's say it's right over here. So when you go, what was going on? So if it's like this, how would you read it? So apparently it's right on 2.9, right? But when you record it, what should you record? You don't want to record it as 2.9. 2.9 centimeter is actually wrong. Why? Because the format is wrong. When your eyes see, it falls right on that line. That means, to your estimation, it's a 0 for the next digit. You have to put that 0 over there. Or in another word, it should be recorded as 2.90 centimeter. Did you notice that? It's 2 digits to the right side of the decimal point as we analyzed in the format of the result. Hopefully this helps. And if it's the same situation over the top, it would be recorded as 2.9 centimeter rather than 2.90, because that 10th position is already estimated. There is no point for the top ruler to estimate 1 extra. Let's do one more example. For example, what if it falls right on this number 5 for top ruler, and for the bottom ruler as well? How would you record the first one over the top? You should record this in the correct format. As we analyze ruler A, which has 0 dp in the smallest increment, so your result should have 1 dp, 1 digit to the right side of the decimal point. So you will not make a mistake if you know that. It would be not 5 centimeter, but 5.0 centimeter. You see that? The format must be correct. That's how you can avoid mistakes, especially in your exams. We test this type of things very often. At the bottom situation over here, if it's right on this line, that means you should record it as 5.00 centimeter. Again, it's 2 decimal places for this ruler. So let's summarize this. How do you make measurements and record the correct number? The first step, find the number of decimal places in the smallest increment of that graduated equipment. Then read one more digit past it. So here's another example. You might think these are different. Actually, in my eyes, they are exactly the same. It's graduated. So in this left side, the graduate cylinder apparently, what's the smallest increment? So 0 is at the bottom, which is usually not listed. Then you have 1 in between this 0 and 1, that's 1 milliliter. But that's not the smallest increment. The smallest increment is between the neighboring lines, how much this represents. So this is a tenth, or 0.1 milliliter. So as we analyze it, the smallest increment is 0.1, don't forget the unit, milliliter. How many decimal places in it? It has 1 dp. So for the result, we do know it must have 1 more dp. So the result with the decimal place on the left side, it depends. It could be 10 point something, could be 1 point something, could be 2 point something, depends on the amount of liquid inside. But to the right side, it must have 2 decimal places or 2 digits to right side of the decimal point. Don't forget the unit. When you read the liquids, you read the lowest point. Usually it's a little bit more exaggerated. Let's exaggerate this a little bit, okay? So that's the lowest point. How would you read this thing? It's the lowest point that you read. Not this one. It's the lowest point that you read, okay? So in this situation, let's read this. Each one represents 0.1. So 1.1, 1.2, 1.3, 1.4, 1.5. It's almost 1.6, but maybe a little bit below 1.6, right? So in this case, you're going to read this as 1.59 milliliter. In reality, though, the lowest point, also called a meniscus, is extremely difficult to determine. So some students might believe, hey, I think that's right on the line of number 6, which is over here. I think if you believe it's right on the line, you would record this as 1.60. Don't forget that 0, because if your eyes determine that it's right on the line, the 0 that tells you it's your estimation, it's on the line. So it's 1.60, or else it would be wrong. And some students, as I said, in reality, and this spacing is not as big, and the lowest point is not easy to determine. Some students might believe this is a 1.61 milliliter. Do you remember the last digit is slightly different? That's why it's estimated. Let's look at the right side. This one actually confuses a lot of people. But if you analyze the equipment first before you make any measurements, you will not make a mistake. First step on the right side, you look at, that's the 0, that's 10. In between 1 and 10, you have 10 increments. So let me just pick out any increment, smallest increment. This would be representing 1 milliliter, not 0.1. So similarly, the first step, in the smallest increment, it has, again, smallest increment. This time I'm going to just write increment, okay? Save some time. Smallest increment, you have 1 milliliter, which has 0 dp in it. All right? So your result should always be 1 more decimal place. So your result, let me write this down. Your result should have 1 dp on the right side. It's milliliter as the unit as well. All right. So to the left side, it could be more or it could be less. So let's read this one. Again, let's exaggerate the meniscus a little bit. All right. So the yellow color is not that clear. So let's read this one. Do you remember now the smallest increment is not 0.1, it's 1. So let's read it. This is 10. That's not 10.1, that's 11. 11, 12, 13, 14, 15. So it's between 15 and 16. So we read it, it might be, to my eyes, it's between 16 and 15. 15 and 16. Okay. So this would be written as 15 point, maybe 0.8, or some might say 15.7, or some might even say, I think it's very close to 16, so you might read it as 15.9 milliliter. Okay? All right, again, it's not the edge that you're reading. So basically, hey, don't read this one, that's wrong. It's not the edge that you're reading. It's the lowest point that you are reading. Hopefully, after these examples, you will have no problem reading. Let's do a similar thing over here. So let's say the meniscus actually, look at the left side, falls right on this number 2. So let's make a meniscus that looks like that way. If to your eyes is right on that line. Similarly, it should be written as 2.00 milliliter, because for this gradual cylinder, as we analyzed, it should have 2 decimal places. On the right side, if it's on 20, let's say it's right on 20 for the lowest point. Let's exaggerate the meniscus a little bit. All right. So if it's right on this line, you would be reading this as 20.0 milliliter. All right. So I think we've had enough examples for this. We just learned how to correctly record the measure numbers. Now let's move on and talk about how to count significant figures. When you try to determine the number of significant figures, first you have to decide what type of numbers you are dealing with. The first type of number is so-called exact numbers. Exact numbers comes from 2 major sources. The first one is by the counting. For example, I have 24 students inside the room. Or you might have 214 students. Or you might have 1,000 students. It doesn't matter. All of them will have unlimited number of sig figs. Or some textbook might say it's useless to talk about the sig figs for those numbers. The second type of exact number comes from the definition. For example, we do know 1 liter is 1,000 milliliter. It's neither 1 sig fig as you see in 1, it's not 4 sig figs either. Rather, it is unlimited number of sig figs. Usually when you see decimal numbers, you would have different type of concept about how many sig figs. You might think, oh, that's 3 sig figs, but it's wrong. Because here, this happened to be an exact number. So 1 inch is exactly 2.54 centimeter, no more, no less. We have another exact number which happens to be a decimal number. I want you to remember both of this. Another one is 1 little cow is 4.184 joule, and this happens to be exact as well. So when you assign the number of sig figs for exact numbers, do you remember they have unlimited number of sig figs? What about the second type of numbers? so-called measure numbers. Measure numbers come from the measurement, as we showed you. You might use a balance to measure the mass. You might use a ruler to measure the length. You might use a gradual cylinder to measure the volume. But no matter how you look at it, they are all measure numbers. For measure numbers, the sig fig counting is actually quite straightforward. Basically, you start counting from left to right and start counting from the first non-zero. That's the key words. First non-zero. Then you count until the end non-stop. Okay? So for example, I might have a number like this, 0.005040 grams. So how many sig figs do you have? Oh, basically I look at the first non-zero. Oh, that's my first non-zero. So 1, 2, 3, 4. So you have 4 sig figs. Notice previously we introduced to you a concept about decimal place. So let's look at that as well. Decimal place, what do you look at first? For decimal place, you look at the decimal point, and it has nothing to do with non-zero or zero. Decimal places are defined as all the digits to the right side of a decimal point. So when you look at it that way, you would have 1, 2, 3, 4, 5, 6 decimal places. So apparently decimal places and the sig figs are different concepts. Let's look at another example. For example, 6.40 kilograms. How many sig figs do you have? First, when you look at that, hey, apparently this looks like a measure number. This is a mass. You measure that using a balance. So what is the sig figs? Oh, you look at the first non-zero. Hey, first non-zero. That's what you look for when you do the sig figs for the measure number. So that's 1, 2, 3. That's 3 sig figs. Let's do another one. How about the number of decimal place? Decimal place, you look at the decimal point. So you have 2 decimal places over here, right? It's quite straightforward. Okay, all right. So when you look at the rules listed at the top, it says start counting from the first non-zero until the end, right? It actually carries a lot of meaning if you want to break it down. For example, all non-zero digits are significant. When you look at the examples we just gave you, yes, they are all significant. And interior zeros, or zeros in between the two numbers, for example, you look at here, look at that 0. Yeah, that is significant. Why? Because it is after the first non-zero. Okay? When you want to break it down, that's what that means. But do you have to? You don't have to. You can just simply start counting from the first non-zero digit, and you never stop until the end. Right? Trailing zeros that fall before a decimal point are significant. So basically, what this tells you is what you look at over here. Yes, yeah, that's the zeros. That's the zeros. They are. Okay? What about leading zeros? Leading zeros, that means the zeros before the first non-zero. Hey, what's the rule about counting the sig fig for the measure numbers? Is start counting from the first non-zero. So anything before the first non-zero, they are not significant. So that does make sense, right? And trailing zeros at the end as a whole number is ambiguous. What does it mean? Oh, this one is actually a little bit different. We're going to go over that in the next step so you know what that means. Trailing zeros at the end of a whole number is ambiguous. Okay, so let's look at that by looking at some examples. So the first example, how many sig figs? Sig figs, you look at the first non-zero. Decimal place, you look at the decimal point. It has nothing to do with zero or not. But for sig figs, you look at the first non-zero. So let's look at this. The first example, number 3 is my first non-zero. You count until the end. So it's 2 sig figs. How many decimal places? For decimal place, you look at the decimal point, that triangle over there. So it's 4 decimal place over here if you really want to write this down. The second one, how many sig figs? Oh, that's my first non-zero here. See, you start counting until the end. That's 5 sig figs. How many decimal place? Decimal place, you look at the decimal point. So that's 4 decimal place for this one as well. Look at next one. 4 sig figs. That's kind of straightforward. How many decimal place? Hey, where's the decimal point? It's over here, which is not written. So it would be 0 decimal place, right? What about this one? Scientific notation. For scientific notation, the number of sig figs depends on the pre-exponent number or the decimal part only. So look at that. That's 4 sig figs. But usually we don't look at the decimal place for scientific notation. All right, look at the next one. 1 dozen is 12. Remember, before you start doing anything, I emphasized, you have to decide the type of numbers. This number is not a measure number. It is an exact number. For this reason, it's unlimited. This is by definition. 1 dozen is 12, no more, no less, no ambiguity. Look at the next number, 100.000 grams. How many sig figs? Sig figs, you look at the first non-zero. Okay. How many sig figs? That would be 6. How many decimal place? When you look at decimal place, you focus on the decimal point, which means you have 3 dp over here. All right. Now look at the next number. You might jump to the conclusion, oh yeah, that's easy, man, that's grams apparently, that's a measure number. Yes, it is a measure number, but this is a special type of measure number. Let's look at the previous slide. Look at the last sentence. The trading zeros at the end of the whole number are ambiguous. So that's a whole number in this 100 grams. And you have trading zeros over here. So the number of sig figs is ambiguous. It's not 3 sig figs. It's not a 1 sig figs either. It's between 1 and 3. Basically, it's the number of sig figs without the trading zeros to with all the trading zeros. Okay? If you want to write this in a more accurate way, for example, if I want to write 100 as 1 sig fig, you would write this as 1 times 10 raised 2 grams. So that's 1 sig fig. If it's 2 sig fig, you write it this way because the pre-expo number will give you the number of sig figs. Or you can write 1.00 times 10 raised to 2 grams. It will give you 3 sig figs. All right. Then when you look at the next example, hey, that's the same. No, that's not the same. Did you notice that? There is a dot, which is a decimal point. So this number is not a whole number. It is a decimal number. So it does not fit the last sentence as you see in this paragraph. So for this one, it's actually 3 sig figs. How many decimal place? 0 decimal place. Okay. Hopefully these examples will help you tremendously in your sig fig counting. All right. Okay. Let's move on and talk about how you should be rounding your results. When you do calculations, sometimes you'll be asked to do the rounding. How do you do it? First, for multi-step, you round only the final answer. Do not round off between steps. We'll show you how you're going to keep the correct number of sig figs or decimal places later on for multi-step calculation. All right. And how do you round it then? If it's 4 or less, you simply drop it, drop that digit. If it's 5 or more, you round it up. All right. A little bit of review before we talk about how to keep the correct result for different calculations in terms of significant figures. So for example, we mentioned in this measure number, which is a mass over here, you have two sig figs, because for sig figs, you start counting from the first non-zero, which is number 3. You have 2 sig fig. And for decimal place, because for decimal place, you look at the decimal point. Similarly, for the second example, you have 4 sig fig, but only 3 decimal places. So for multiplication or division, your result should keep the fewest number of sig figs. However, for for plus or minus, the addition or subtraction, you would keep the fewest decimal place. All right, so that's why previously we have introduced to you the difference of significant figures SF and the decimal place dp. So let's look at some real examples. In the top example, this is a division. So how should you keep your result? Do you keep the fewest sig figs or the fewest decimal place? Oh, it's fewest sig figs that you keep. So for this reason, we count the sig figs. First non-zero, 1, 2, 3, 4. 4 sig figs, and the second one has 3 sig figs. Your calculator gives you this number, 0.96590. You got to keep 3 sig figs. Do you remember 3 sig figs? You got to start counting from the first non-zero. So that's my 1. Hey, I did not look at the decimal point. No, I did not. I look at the first non-zero when I count sig figs. Okay, it happens to be the first digit as well, but the meaning is totally different. So you have 1, 2, 3. That means you have to round it to this number 5. So you will have 3 sig figs. The next digit after 5 is 9, which is greater than 5. That's why you round it up to 0.966. All right. Look at the next example. It's an addition. For addition, you look at the number of decimal places. Sometimes to help you do that, you can line up the decimal point. So the shortest one or the smallest number of decimal place is what you keep. So you add it together, you have 9.214. The first one you have 2 decimal place. The second you have 3 decimal place. The next one 3 decimal place as well. So your result is 2 decimal place. You round it from 9.214. The 4 is smaller than 5. You drop it. So that's it. All right. Now let's talk about how you round it in the multi-step calculation. Do you remember in multi-step calculation, you never round it in the middle. But let's see how we can still keep the correct number of sig figs or decimal places. So when you have a calculation like over here, the first step is always going to be the calculation in the parentheses. Right? In this parentheses, it's a subtraction. So you keep the correct number of decimal place, not significant figures. When you do the calculation, if you rewrite it, it would be 3.489, just keep it as is, times 3.37. That's what your calculator tells you. And for this step, you keep the fewest number of decimal place, which is 1 decimal place, because 5.67 is 2 decimal place. Is 2 decimal place over here, and the 2.3 is 1 decimal place. So that's why you keep 1 decimal place. But why do we write 3.37? Because you don't want to round it off in the intermediate steps. Rather, we're going to underline this so we know that 3 is the last significant number you should record. Okay? I know subtraction goes by decimal place, but 3 is the last digit or the last significant figure that you're going to keep. So for the next step, apparently it's multiplication. When you use your calculator gives you 11.758. Do you remember this step is multiplication? Multiplication goes by sig figs. The first number in the box, apparently this one has 4 sig figs. The second one, remember, that's not 3 sig figs because the 3 over here is the last digit as we underlined, so that's 2 sig figs. So your result, 11.758, should be rounded to 2 sig figs, and that means you round it to this number 1 over here. So when you record it, it becomes 12. Okay? The whole procedure is explained in much detail on this page. So you can also read it on your own. Okay, all right. Now let's do multiple choice. So in this calculation, I hope you can use how to use your calculator correctly. Okay, in the first step, as you see over here, apparently this is 2 scientific notation divided by each other. It goes by sig figs. So scientific notation, the sig fig depends on the decimal part only. That's 3 sig figs, and that's 4 sig figs. So your result will be 4 versus 3. So your result will be 3 sig figs for sure. So you do the calculation and it should give you the correct number. Your calculator, I just did a calculation, your calculator gives you a number 1.5049 etc. times 10 raised to 15. Do you remember? You're going to keep 3 sig figs. That's first non-zero, 2, 3. So you round it to that 0. The next one is actually 4, smaller than 5. Okay, so you round it to 1.50 times 10 raised to 15, which is A. Right. So let's summarize everything we just talked about. About the numbers, first, you got to know how to record the correct numbers when you make a measurement. The measurement goes by your equipment. The first step of your measurement, you find out the smallest increment in that equipment. Then the second step, read one more digit past it. Never start any measurement without analyzing the equipment first. Always analyze your equipment first so you know what format of your result will be. All right. Next thing, we talk about how to count sig figs. For sig figs, you pay attention to the first non-zero digit, then start counting until the end. There is one special case, which is the whole numbers with trailing zeros, which has ambiguous number of sig figs. And for the second type of numbers, which is so-called exact numbers, for example, the numbers that come from counting, the numbers come from definition, they are so-called exact numbers, and they have unlimited number of sig figs. Next, we talked about how to keep the correct number of sig figs in your calculation. For multiplication or division, you pay attention to sig figs. You keep the fewest number of sig figs. For plus or minus, you keep the fewest number of decimal places. So, basically that's everything you need to know about a number. We do know for any measurement, not only you should keep the correct number, you should also have the right unit for it. there are 7 so-called SI base units. From these 7 base units, all the other numbers can be derived. You have to memorize these numbers. For example, you have to memorize these units. For example, second is the SI unit or SI base unit for time. It's not hour, it's not minute. If I ask you what's the SI base unit for temperature, it's not Fahrenheit, it's not Celsius, it's Kelvin. And SI base unit for mass is going to be kilogram. All right. So that's the first aspect about the units. There's 7 SI base units. You have to memorize it. Next, for some big numbers or small numbers, as we learned, we can use scientific notation to represent it, or we can do something on the units. So we can put a prefix before that unit. For example, when you look at centi, centi means it's 100th or 0.01, right? So 1 centimeter can be written as 1 times 10 raised to negative 2 meter. Hey, look at that. You see, that's what this means, okay? So let me rewrite. 1 centimeter equals 10 raised to negative 2 meter. 1 is the same, meter is the same, right? So this C is the same as 10 raised to negative 2. That's how you can avoid making mistakes. All right. You have to memorize all of this. For example, if I ask you how much is 1 microgram? 1 microgram. Well, 1 microgram, this mu is actually the same as 10 raised to negative 6. So 1 microgram would be the same as 1 times 10 raised to negative 6 grams. Or you can simply write 10 raised to negative 6 grams. All right. Okay, memorize these things. Let's do a quiz on this. So what represents 10 raised to negative 9? Oh, that's nano. Okay. All right, go ahead and memorize all those things. So next, we'll be talking about one of the most important topics of this chapter, which is how to convert one unit to another. During the past, before you take this course, you might have been asked to convert one unit to another already. For example, I'm going to ask you how many centimeters in 4.654 inch. During the past, you do know one thing. 1 inch is 2.54 centimeter. So when you do a calculation, you say, 1 inch is 2.54. We have this many inches. So that's multiplication. So that's what we do. So you do 4.654 inch times 2.54. All right. So basically, this will give you how many centimeters over here? The result is 11.82116. 11.82116. Hey, do you remember 2.54? That's exact number. So it has unlimited number of suffix. Okay? It's not 3 suffix. It's unlimited number of suffix. So when we keep the number of suffix, this is 4 suffix. The other one is unlimited. So you keep 4 suffix. When you round it, it will be 11.82, not even 11.8. No, not 11.8. It's 4 suffix that you keep. So that's how many centimeters. But I'm going to introduce to you a different way to do the calculation. All right. So basically, we do know 1 inch is 2.54 2.54. So for this reason, the ratio between 1 inch and 2.54 is 1. And if you put 2.54 centimeter over the top, 1 inch at the bottom, the value is also 1. So if I can do this calculation in similar way, for example, I ask you how many centimeters in 4.654 inch. If I have this to begin with, if I multiply 1, of course it will be exact the same as the original, right? But we do know, what is this 1 over here? The 1 can be one of these two ratios. So I'm going to write it differently. So if I write 2.54 at the bottom and this is centimeter, okay, 1 inch at the top. So this, technically speaking, that is correct. But you notice that this is inch, here is centimeter. You will not be able to cancel it out. But the number and the unit combination will still be correct. But it's not the one we desire, because we want to find out how many centimeters you have. So for this reason, we're going to do the same way. Inch times 1 inch is 2.54 centimeter. Okay? Because this value is what? Is 1. So it will not change the total value. But when you do the calculation, the inch and inches cancel out. The top is centimeter, which remains. So after you do the calculation, of course, it will also give you 11.82 centimeter. So if you use something like this or that, we call this kind of unit analysis dimensional analysis. Okay? All right. So let's look at one more example. For example, I ask you, how do you convert 44.7 centimeter to inches? So when you do this calculation, basically, I would like to rewrite this. So basically, in this, you have the centimeter. We want you to convert to inch. How do you do that? You start with your quantity over here. So if I set it up without writing the numbers, actually, it might be more helpful in the future. So if centimeter, you start with times whatever relationship you have over here. You do remember, only if you have centimeter to begin with, you can cancel it out, right? So, but what numbers do you need to put down in those places? So for the first one, what should I put down? Oh, that's what you started with, right? So it would be 44.7, 44.7, right? Now what is the second thing? These are so-called conversion factors, which have values of 1. So what is the relationship between inch and centimeter? It's 1 versus 2.54. Why do you put 2.54 at the bottom? Because it's centimeter that is associated with it. When you put it this way, centimeter will be cancelled out, and you will have inch as the final unit. That's why you have the results over here. So hopefully this helps. Do remember, 2.54 is exact number. So it has unlimited number of sig figs. So the sig fig will go by 44.7. Okay, so you have 3 sig figs that you keep. So you have 17.6 as the correct answer. Okay. All right. This is one of the most simple version of unit conversion. So I write it in this way. So you can either convert centimeter to inch, or you can convert inch to centimeter. It's basically one-step procedure. Okay. What if two units are not directly related? For example, hey, how do you convert centimeter to feet. So when you write this thing, because most of, if it's not provided, the information is not provided, you say, hey, what is the relationship between centimeter and foot? You don't have the direct relationship, which means you cannot convert this in one step. So what you are going to do is to find the intermediate step or the bridge to connect these two units. We do know centimeter is related to inch, which means centimeter can be converted to inch, and inch is connected to feet. So that's why you have the solution map listed like this. So how do you do the conversion? Let's do it the same way. Don't write the numbers yet. You start with centimeter. That's what you start. So you have centimeter times the first step, and write number 1 here. First step, it's the relationship between centimeter and inch. So you want to cancel out centimeter. That's why you have centimeter at the bottom, inch at the top. That's the first step. We're going to put down the numbers later on. Don't worry about it, okay? So the second step is converting inch to centimeter, because after the first step, you have inch. Look here. You see the dot, moving dot over here. So that's inch that is remaining, okay? Now you're going to convert inch to foot. See? Inch for the next step is canceled out, right? So this gives you foot as the unit. But what numbers do you put in? You always start with what is given, which is you are given 194, see, right, 194 centimeter over here, all right? So the next step, what numbers do I put over here? It always goes by the real numerical relationship. You do know 1 inch is 2.54 centimeter. So that's why 1 is at the top, 2.54 is at the bottom. Okay? Now the second step, 1 feet is 12 inch. Okay? How do you keep the number of sig figs? Do you remember that's 3 sig figs, and you look at that, that's exact. That's unlimited. Unlimited. That's by definition. Similarly, that's also unlimited. 1 feet is 12 inches, no more, no less. That's unlimited. So that's why it's not 2 sig figs that you keep. It's 3 sig figs that you keep. Okay? All right. Hopefully these details will help you understand how to do a multi-step unit conversion. The key is to find the intermediate unit that can connect the corresponding initial and the final units. Next, we're going to discuss a different type of calculation, which is the units that is raised to a certain power. For example, it might be squared, might be cubed. In this case, it's cubed. So how do you convert? We do know, for example, you have a centimeter over here. We do know how to convert centimeter to inch. As we explained, you start with certain centimeter and then times the conversion factor. So centimeter cancels out. But if it's cubed, it's slightly different. Do remember, 2.54 is the same as 1 inch. So if you write it this way, like 2.54 centimeter cubed, and you think it's the same as 1 inch cubed, that's wrong. That's not correct. It's this whole thing, 2.54 as a whole, that is the same as 1 inch. So you must cube the whole thing to make them the same. All right? So the numbers are cubed and the units are cubed. You see that? So when you do the calculation, we can write it this way. All right? How many inches do you, how many cubed centimeter you have? It's 1255. Let's write this again. So you're going to convert this to inch cubed. All right. You started with what is given. And now you convert it. But how do you write this whole thing? Remember, 1255 is what is given. Don't cube this thing. You look at that, that's not cubed, right? But for the relationship, it's the whole thing cubed, or you can separate it, the top and bottom. That would be how many inches? It's 1 inch, and here's 2.54. Okay? Notice this in the box is exactly the same as this one. They are equivalent because you simply do the calculation of this 1 cubed and 2.54 will give you a 16.387. Okay? So you do this calculation, you will end up with exactly what you see over here. All right? Okay. Let's do maybe one more example. For example, how do you convert, let's say, 2.105 centimeters squared. I want you to find out how many inch squared you have. Okay? So if you do the solution map, it would be, hey, I want to convert centimeters squared to inch squared. Okay. So you write this cm squared first. That's what you're given. Now you're going to write the correct conversion factor. Do you remember you must have cm squared at the bottom, right? Okay. But it's the whole thing that is squared. It's 2.54. The whole thing is squared, and the 1 inch at the top, this whole thing is squared. When you do the calculation, so that would be 2.105. So when you do this calculation, it will give you a number that has this 2.54 squared, 1 squared as well. So let me do this calculation right now. The result is 0.3263 for sig figs, because these are exact numbers. They have unlimited number of sig figs. So I'll keep the correct unit. Oh, so centimeter actually is cancelled out. So this is an inch squared. Okay. All right. We have one more topic to talk about, which is density. So density is a physical property that can be measured without changing the identity itself. You simply measure the mass and the volume and divide the mass by volume. You would have the density. All right. For example, you have a sample of liquid that has a volume of 22.5 milliliter and the mass of 27.2. So we ask you to find the density. You simply do mass over volume and keep the corrective sig figs, which is 3 sig figs, and don't forget the unit. So grams divided by milliliter, that gives you grams per milliliter, 1.21. Okay. Look at one more example. Find the mass of lead that has a density of 11.4 grams per milliliter and displaces certain volume. So what is the mass? We do know D is M over V. So M would be D times V. When you do this calculation, so substitute numbers in. So what is D? It says it's 11.4, okay, grams per milliliter. It's at 20.1 milliliter. You cancel this out. Apparently, they'll give you A as the correct answer. Okay? All right. Yeah, actually, we have one more example. Identify an unknown object that has a mass of the certain number and displaces certain volume. So how do you identify this? You need to calculate the density, right? So let's do that. So density equals mass over volume. Do pay attention to the units. Remember, in this table, you have grams per centimeter cubed. So you will have to convert this 1.08 kilograms to grams. It's 1.08 times 1,000, right? or 10 raised to 3 grams divided by the units over here. It says it's the same, so we don't need to convert that one. It's 0.5 centimeter cubed. So let's do this calculation. So it turns out it's 21.4 grams per centimeter cube. So that is platinum, which is the correct answer. All right, that's it for today. Hopefully you've been having fun. If you have any questions, you can visit my office hour, online office hour, using Pronto IM. Check your syllabus for the details. Thank you. Have a good day.